A star burns in the constellation Orion, a red glow pulsing against the black canvas of space. Betelgeuse, a supergiant 600 light-years distant, has captivated human eyes for millennia. Its light, leaving its surface 6 centuries ago, carries secrets of a stellar life nearing its end. Astronomers watch it now, noting flickers and fades, a rhythm that hints at an imminent cataclysm. This star, 15 times the mass of our sun, has lived a brief, ferocious existence, consuming its fuel in 10 million years, a cosmic sprint compared to our sun's steady marathon. Its surface, vast enough to swallow Jupiter's orbit, churns with heat and instability, a furnace radiating 100,000 times the sun's power. In recent years, Betelgeuse has stirred. It dimmed sharply between 2019 and 2020, losing 2/3 of its brightness, an event astronomers called the Great Dimming. Telescopes trained on its surface saw clouds of dust, perhaps ejected during a massive convulsion, obscuring its light. Then it flared again, pulsing brighter, its cycles erratic. These changes, tracked by observatories like the Atacama Large Millimeter Array, reveal a star in turmoil. Its core, fusing heavier elements like carbon and oxygen, approaches a critical threshold. When it reaches iron, fusion will falter, and gravity will seize control, collapsing the core in seconds. Such a collapse could birth a supernova, an explosion so luminous it might rival the moon's glow in Earth's sky, visible day and night. It would outshine Sirius, the brightest star we know, lingering for weeks, 600 light-years away. Betelgeuse poses no threat. Its gamma rays and cosmic radiation will dissipate before reaching us. Yet its proximity, in cosmic terms, makes it a spectacle humanity hasn't witnessed since the supernova of 1604, observed by Johannes Kepler. That event, 6,000 light-years distant, dazzled Europe's skies. Betelgeuse, 10 times closer, promises a brighter show. The star's rotation complicates predictions. Spinning once every 20 years, its surface moves at 18,000 kilometers per hour, far faster than expected for a supergiant. This speed, measured through Doppler shifts blue light from the approaching side, red from the receding, suggests a past upheaval. Some propose Betelgeuse devoured a smaller companion star, its gravity pulling in material that spun it faster. Nitrogen in its atmosphere, a sign of deep mixing, supports this idea. Simulations show a companion spiraling inward, merging in a burst of friction and heat, leaving Betelgeuse altered. This merger theory reshapes our view of the star's mass. If Betelgeuse began as a single star, it might have 10 to 15 solar masses, destined for a supernova and a neutron star remnant. But a merger could push it toward 20 solar masses, where collapse might form a black hole, perhaps without a visible explosion. The star's distance, uncertain by tens of light-years, clouds these calculations. Without precise measurements, its fate remains a gamble neutron star or black hole, supernova or silent vanish. Astronomers trace Betelgeuse's pulses, cycles of brightness spanning 1 year and 6 years, to internal convulsions or a hidden companion. Computer models suggest a star, nicknamed Beetle Buddy, orbiting close enough to tug at Betelgeuse's outer layers. Its gravity could stir the supergiant's surface, amplifying its pulses. Direct evidence awaits the supernova itself, when debris patterns might reveal a companion's influence. Until then, observatories scan for subtle shifts in light, hoping to catch the rhythm of this cosmic dance. Humanity's watch began long ago. Ancient Egyptians saw Betelgeuse as a marker in Orion, guiding their myths. Today, backyard telescopes track its flickers, while global networks of professionals analyze its spectra. The star's youth, 10 million years old, means no rocky planets likely orbit it, their formation outpaced by its rapid burnout. Yet its death could seed the cosmos with elements like oxygen and iron, forging the raw materials of future worlds. As Betelgeuse nears its end, it draws us to the sky, a reminder of stars as engines of creation and destruction. The sky above Orion shifts as Betelgeuse pulses, its red light a beacon across 600 light-years. Its behavior flaring, dimming, spinning defies simple models of stellar death. Astronomers, peering through arrays like the Very Large Telescope, see a star stretched to its limits. Its diameter, nearly 1 billion kilometers, dwarfs our suns. If placed at the sun's center, Betelgeuse's edge would engulf Mars. This scale, measured by interferometry combining light from multiple telescopes, reveals a surface roiled by convection. Giant cells of gas rising and falling, like storms on a distant sea. The Great Dimming of 2019 puzzled observers. Betelgeuse faded to its faintest in a century, sparking talk of an imminent supernova. Data from the Hubble Space Telescope pointed to a massive ejection, a cloud of silicate dust blocking its light. This outburst, tied to a convective surge, hinted at instability deep within. The star's core, now fusing silicon into iron, nears a breaking point. Each fusion stage, hydrogen to helium, helium to carbon, releases less energy, accelerating the countdown. Iron, the final stage, marks the end. Its fusion absorbs energy, starving the core of pressure to resist gravity. A supernova's mechanics unfold in moments. The core, denser than Earth's crust, collapses to the size of a city. Protons and electrons merge into neutrons, releasing a flood of neutrinos, ghostly particles that escape the star, carrying away energy. This implosion rebounds, launching a shockwave that tears through the outer layers. The explosion, brighter than a billion suns, scatters elements forged in the star's heart. Betelgeuse's supernova could peak at a luminosity of 2 times 10 to the 38th watts, 500 billion times the sun's output. For weeks, it might shine as a second sun, visible even at noon. Yet the star's mass holds the key to its fate. At 15 solar masses, it would likely form a neutron star, a remnant 10 kilometers across. Denser than an atomic nucleus, a teaspoon of its material would weigh 1 billion tons. If heavier, near 20 solar masses, the collapse might not stop. Neutrons, crushed beyond endurance, would yield to gravity, forming a black hole. This singularity, warping space itself, could swallow the star's light, leaving no trace. Simulations struggle to pin down Betelgeuse's mass, as its distance 550 to 650 light-years varies in measurements. The star's rapid spin, 5 kilometers per second at its equator, adds another layer. Most supergiants rotate slowly, their expansion diluting angular momentum. Betelgeuse's speed suggests a violent past. A companion star, perhaps half the sun's mass, could have merged with it millions of years ago. As it spiraled inward, friction heated the supergiant's envelope, boosting its rotation. Nitrogen, dredged from the core, now enriches its surface. A chemical scar of this merger. Such events, rare but not impossible, reshape a star's evolution, pushing it toward a heavier, black hole-bound fate. The companion theory extends to Betelgeuse's pulses. Its brightness cycles, 1 year and 6 years long, mirror a heartbeat. Models suggest a low-mass star, Beetle Buddy, orbiting at a distance where its gravity tugs the supergiant's outer layers. This interaction could amplify convection, driving brightness swings. Telescopes like ALMA search for spectral shifts, hints of an unseen partner. If present, its orbit would imprint on the supernova's debris, a final clue to Betelgeuse's story. Without direct detection, the companion remains a hypothesis, testable only when the star explodes. Beyond Betelgeuse, the galaxy teems with stars on similar paths. Rigel, Orion's blue giant, burns hotter but younger, its supernova millennia away. Antares, in Scorpius, mirrors Betelgeuse's red glow, another candidate for a near-future explosion. These stars, born in clusters, forge elements that drift into nebulae, birthing new systems. Betelgeuse's death will enrich its region, its shockwave compressing gas clouds to spark star formation. Iron from its core could one day form the hearts of planets, a cycle spanning billions of years. The James Webb Space Telescope, launched in 2021, peers at Betelgeuse in infrared, piercing its dust veils. Ground-based arrays, like the Square Kilometer Array, map its radio emissions, tracing gas outflows. Amateur astronomers, armed with backyard scopes, log its brightness nightly, their data feeding global databases. This collective watch, blending professional and citizen science, captures a star at its tipping point. The supernova, when it comes, will flood detectors with neutrinos, light, and gravitational waves, a multi-messenger event rewriting stellar physics. The star's distance ensures safety. At 600 light-years, its radiation gamma rays, X-rays will scatter harmlessly. A supernova within 100 light-years could strip Earth's ozone, but Betelgeuse lies far beyond this zone. Its light, though dazzling, will pose no risk, a spectacle for all to witness. Ancient observers, from Babylonians to Polynesians, charted Orion's stars, unaware of their fates. Today, we stand ready, telescopes poised, to capture a moment that may already have happened, its light still racing toward us. Betelgeuse's glow flickers in Orion's shoulder, a star on the edge of oblivion. Its pulses, tracked by astronomers worldwide, hint at a deeper cosmic rhythm. Beyond its surface, the galaxy churns with stellar encounters, some close enough to reshape our solar system's fringes. A star, smaller than the sun, passed within 110 astronomical units 11 billion kilometers billions of years ago. This flyby, closer than Voyager 1's current distance, stirred the outer solar system, leaving clues in the orbits of distant objects. Trans-Neptunian objects, icy bodies beyond Neptune, hold these secrets. Sedna, a dwarf planet 937 astronomical units from the Sun, follows an elliptical path, its orbit stretched by an ancient tug. Two others, moving retrograde opposite the planet's motion, defy the solar system's order. Over 3,000 simulations, run on supercomputers, trace these anomalies to a stellar flyby. A star, 8/10 the Sun's mass, grazed the Sun's domain, its gravity nudging icy bodies into chaotic paths. This encounter, 4 billion years ago, also explains irregular moons like Saturn's Phoebe, captured from the Kuiper Belt. The Oort cloud, a spherical shell of comets encircling the solar system, felt the star's pull. Stretching a light-year outward, this reservoir of ice responds to passing stars, sending comets inward. Such events, occurring every few 100,000 years, pepper the inner planets with impacts. Earth's craters, like Chicxulub, tied to the dinosaur extinction, may owe their origins to distant stellar nudges. The flyby's legacy lingers, a reminder of the galaxy's crowded highways, where stars cross paths over eons. Closer to home, the Sun drifts through a vast cavity, the local bubble, spanning 1,000 light-years. This region of hot, low-density gas formed 10 million years ago when supernovae erupted nearby. Their shockwaves carved a void, compressing gas at its edges to birth new stars. The Sun, entering this bubble 5 million years ago, now floats near its center, a cosmic coincidence. Telescopes like Eurosita, orbiting 930,000 miles from Earth, map this bubble's contours, revealing an asymmetry hotter and denser above the galactic plane. A tunnel, carved through the bubble's cooler gas, points towards Centaurus, discovered by Eurosita's X-ray scans. This structure links the local bubble to distant regions, perhaps the Gum Nebula or molecular clouds. Astrophysicists propose a network of such tunnels, hot gas channels threading the galaxy's interstellar medium. First theorized in 1974, this idea gains traction as Eurosita's data shows the tunnel's edges, glowing with million-degree plasma. The Sun's passage through this network shapes its environment, influencing star formation around us. Betelgeuse, too, exists within this galactic tapestry. Its supernova, when it arrives, will ripple through the local bubble, its shockwave mingling with ancient remnants. The star's mass loss, already underway, sheds gas that cools into dust, seeding the interstellar medium. Observations from the Very Large Array show these outflows, streams of carbon and oxygen that will outlive the star. This material, forged in Betelgeuse's core, could collapse into new stars, a cycle driven by the galaxy's relentless churn. The star's variability, its 1-year and 6-year cycles, draws scrutiny. Photometric data, collected over decades, shows brightness swings tied to convective cells, bubbles of gas larger than Earth's orbit. A companion star, orbiting at 10 astronomical units, could modulate these cycles, its gravity stirring the supergiant's envelope. Spectral lines, split by Doppler shifts, hint at this partner, but confirmation awaits higher resolution scans. The supernova's ejecta, if asymmetric, might betray this companion's presence, a final signature of their dance. Humanity's gaze extends beyond Betelgeuse to other stellar remnants. T Coronae Borealis, 2,600 light-years away, prepares for a nova, a white dwarf, paired with a red giant, accretes hydrogen until it ignites, flaring 1,500 times brighter every 80 years. Its last eruption, in 1946, followed a predictable pattern, a brightness spike in 2015, a dip in 2023. Astronomers, alerted by amateurs, expect its next flare soon, a fleeting glow visible without telescopes. Unlike Betelgeuse's supernova, T Coronae Borealis's nova spares the star, restarting the cycle. Its white dwarf, Earth-sized but sun-massive, pulls gas from its companion, triggering thermonuclear blasts. These events, observed since 600 BCE, mark the binary's rhythm. Amateurs, scanning the northern crown, may spot the next eruption, their alerts triggering global observatories. The nova's shell, expanding at thousands of kilometers per second, glows briefly, a cosmic firework in the galaxy's vast arena. The galaxy's edges hide stranger forces, micro-quasars, like V4641 Sagittarii, 20,000 light-years away, mimic distant quasars, a black hole, 6 solar masses, devours a 3 solar mass star, launching jets at near-light speeds. These jets, aligned toward Earth, appear to move 9 times faster than light, a relativistic illusion. The Hawk Observatory, in Mexico, detects their gamma rays, photons at 200 tera-electron volts. These energies, once tied to galactic cores, now emerge from our cosmic backyard, rewriting models of cosmic ray acceleration. V4641, Sagittarii's jets pierce the galactic void, their gamma rays a beacon from 20,000 light-years. These microquasars, compact binaries of black holes and stars, challenge assumptions about cosmic radiation. Unlike supermassive black holes in galaxies like Markarian 231, 500 million light-years distant, microquasars operate on human timescales, their jets flaring over days. HAWC's water tanks, nestled beneath a Mexican volcano, capture these photons, revealing energies 10,000 times beyond typical stellar emissions. This discovery ties local systems to galaxy-scale processes, a bridge between the near and far. Betelgeuse, closer at 600 light-years, looms as a counterpoint. Its supernova, unlike a microquasar's jets, will be a singular event. Its core, now fusing silicon, nears collapse. Neutrinos, streaming from this implosion, will reach Earth first, detected by underground observatories like Supercameo Conde. Light will follow, a blaze visible across continents. The explosion's shockwave, traveling at 10% light speed, will carry iron, oxygen, and gold, elements forged in the star's heart. These will drift, perhaps forming nebulae where new stars ignite. The star's rotation, measured by ALMA's sub-millimeter arrays, remains a puzzle. Its 5 km/s spin, faster than most supergiants, suggests a merger. Simulations show a companion star, 1 solar mass, spiraling into Betelgeuse's envelope 2 million years ago. The friction, heating gas to millions of degrees, spun the supergiant faster, mixing nitrogen to its surface. This event, modeled on supercomputers, altered Betelgeuse's path, potentially tipping it toward a black hole. Without the merger, it might have followed a neutron star's fate. The local bubble, enveloping Betelgeuse and the Sun, shapes their stories. Formed by supernovae 14 million years ago, its hot gas 10 times hotter than the Sun's surface expands unevenly. Earocita's X-ray maps show a tunnel toward Centaurus, a conduit of plasma linking bubbles across the galaxy. This network, threaded through cooler gas, channels energy from ancient explosions. The Sun, drifting through this cavity, passes star-forming regions at the bubble's edge, their glow visible in ultraviolet. Stellar flybys, like the one 4 billion years ago, connect to this galactic churn, the rogue star, grazing 110 astronomical units, reshape the Oort cloud. Comets, dislodged by its gravity, still trickle inward, some striking Earth. The flyby's influence extends to Jupiter's irregular moons, captured from the Kuiper belt. simulations, run at institutions like Caltech, model these encounters, showing how a star's passage ripples through a system. Such events, rare but inevitable, underscore the galaxy's dynamic nature. T Coronae Borealis, in the Northern Crown, offers a gentler spectacle. Its white dwarf, accreting hydrogen, nears another nova. The cycle, repeating every 80 years, follows a rhythm: a high state in 2015, a dip in 2023. Amateurs, scanning with 10-inch telescopes, may catch the flare, alerting observatories like Keck. The nova's shell, expanding at 2,000 kilometers per second, will glow for days. A contrast to Betelgeuse's weeks-long supernova. Its binary dance, observed since antiquity, links humanity's past to its present sky. Primordial black holes, relics of the Big Bang, add a darker thread, smaller than atoms but asteroid massive. They race through space at 25,000 kilometers per second, passing through the solar system every decade. They nudge orbits subtly. A flyby near Mars could shift its path by centimeters, measurable by NASA's orbiters. The 1908 Tunguska event, flattening Siberian forests, sparks debate: meteor or micro-black hole hawking radiation. Eroding these holes suggests they've dwindled, but precise tracking of Mars's orbit could confirm their existence. Microquasars like V4641 Sagittarii tie these threads together. Their jets, mimicking quasars, accelerate protons to near-light speeds, flooding the galaxy with cosmic rays. HAWC's detections, paired with radio telescopes, map these jets, showing a black hole orbiting a star every 3 days. This system, in Sagittarius, mirrors processes in distant galaxies, offering a laboratory for astrophysics. Its photons, traveling 20,000 years, reach us now, a signal of the galaxy's violent undercurrents. Betelgeuse's story weaves through this cosmic web. Its pulses, driven by convection or a companion, ripple across its surface. The 6-year cycle, longer than most supergiants, suggests deep structural shifts. Photometry from the American Association of Variable Star Observers tracks these swings, feeding models at institutions like MIT. The star's dust clouds, imaged by the Gemini Observatory, obscure its light, complicating predictions. When it explodes, its light will flood these instruments, a dataset spanning centuries. The galaxy spins, a spiral of 200 billion stars, each a story of birth and death. Betelgeuse, pulsing in Orion, nears its end, its red light a signal across 600 light-years. Its supernova, perhaps a neutron star's birth or a black hole's silent collapse, will mark a moment humanity may witness bare-eyed. The star's rapid spin, nitrogen-rich surface, and erratic pulses tied to a possible merger or companion paint a portrait of chaos. Telescopes, from backyard scopes to the James Webb, stand ready, their data a bridge between ancient light and modern eyes. T Coronae Borealis, 2,600 light-years away, prepares a quieter flare. Its white dwarf, feeding on a red giant, will nova soon, repeating a cycle seen in 1946. Amateurs, scanning the Northern Crown, may spot it first, their alerts triggering a global watch. The nova's glow, lasting days, contrasts Betelgeuse's weeks-long blaze, yet both tie humanity to the sky's rhythms. Their light, delayed by centuries, reminds us we see the past, a cosmic archive unfolding nightly. The local bubble, 1,000 light-years wide, cradles these stars, formed by supernovae 10 million years ago. Its hot gas and Centaurus tunnel reveal a galaxy threaded by plasma channels. The sun, drifting through this cavity, passes star-forming clouds, their light a faint glow in ultraviolet. Rosita's X-ray maps, built from orbits beyond Earth's geocorona, show this bubble's asymmetry, a testament to ancient explosions. Betelgeuse's shockwave, when it comes, will ripple through this space, joining a cycle of creation. Stellar flybys, like the one 4 billion years ago, shape this cycle. A star, grazing 110 astronomical units, stirred Sedna's orbit in Phoebe's path, its gravity a sculptor of chaos. The Oort cloud, nudged by such encounters, sends comets inward, their impacts etched on Earth's surface. Simulations, tracing these paths, show the galaxy's crowded nature, where stars brush past every million years. These events, subtle but profound, link the solar system to its neighbors. Microquasars, like V4641 Sagittarii, add a violent pulse, their jets, firing gamma rays at 200 tera-electron volts, mimic distant quasars. HAWC's detections from Mexican mountaintops reveal a black hole devouring a star, its light a 20,000-year journey. These systems, scattered across the Milky Way, drive cosmic rays, seeding the galaxy with energy. Their processes, scaled down from galactic cores, offer a window into the universe's engines, a parallel to Betelgeuse's explosive fate. Primordial black holes, Big Bang relics, weave a final thread, racing at 25,000 kilometers per second. They may graze the solar system, nudging Mars's orbit by centimeters. The Tunguska blast, a Siberian mystery, hints at their passage, though meteors remain the likely culprit, tracking asteroids with telescopes like Pan-STARRS. Astronomers seek these ghosts, their influence a whisper in orbital data. If real, they tie the solar system to the universe's dawn, a link across 14 billion years. These stories, Betelgeuse's collapse, T Coronae's flare, the local bubble's tunnels, flybys, microquasars, and black holes converge in the galaxy's dance. Each event, from a star's death to a comet's fall, shapes the cosmos we see. Humanity, watching from a rocky planet, charts this dance with tools and wonder. Babylonians, 6 centuries BCE, saw the same stars, their clay tablets marking orbits. Today, we parse their light with silicon and steel, yet the sky's questions endure. Betelgeuse's light, when it flares, will join this archive, a chapter written in fire.
What does it mean to say the universe is expanding? Where does it expand? And what lies beyond it? For centuries, we've tried to chart the contours of reality, guided by ancient geometry, modern physics, and the strange behavior of light itself. This journey explores the deepest riddles of space, time, and the architecture of the cosmos, revealing not just where we are in the universe, but what the universe might truly be. Bending the straight line. The idea that parallel lines never meet was long held as self-evident truth, a cornerstone of the logical framework laid by Euclid in his writings on geometry more than 2,000 years ago. According to his fifth postulate, if you draw 2 lines that never cross, and you extend them forever, they should still never meet. It seemed like a perfectly reasonable assumption. But there was one persistent problem while the other axioms of Euclid's geometry were readily proven or applied. This one resisted all efforts. Mathematicians tried for centuries to prove it, and yet no one could. Not because they lacked skill, but because the postulate may never have been universally true at all. In the 19th century, a revelation emerged that upended everything. By assuming that the parallel postulate might be false, mathematicians began to explore new geometries, curved spaces where parallel lines could, in fact, meet. This idea was not merely mathematical mischief. It cracked open the door to a deeper truth about the universe itself. Because once you abandon the belief that space is always flat, you begin to realize it might be warped, twisted, or stretched in ways that defy common intuition. Non-Euclidean geometry became the foundation for understanding curved surfaces and eventually curved space. Imagine 2 trains racing along tracks that seem parallel at every glance, running side by side as steel wheels grind forward. But if the surface they move on is curved, Then, over great distances, those tracks might bend toward each other. On a sphere, such as Earth, two lines of longitude start far apart at the equator and converge at the poles. The parallel postulate fails in such curved settings not because the lines changed their behavior, but because space itself isn't as straight as it once seemed. This realization is not just about math, it's about the very shape of reality, because space is not simply the empty stage where the universe plays out. It is an actor too, capable of changing shape, exerting influence, and even growing over time. Our journey through these warped geometries begins not in a laboratory but in ancient times, with the first shadows of scientific thought. One of the most striking figures in this story was not a physicist but a 13th century bishop named Robert Grosseteste. Long before cosmology had equations, Grosseteste envisioned the birth of the universe as an eruption of light, an expansion from a single point where radiant beams poured outward, then condensed into matter. He lacked the tools of modern astronomy. Yet his ideas echoed those that would one day form the basis of the Big Bang. Though his worldview remained entangled with theology, Grosseteste insisted that light and geometry held the secrets of creation. He believed that to understand the origin of the cosmos, one must study the behavior of light itself. It was an astonishingly prescient view. Centuries later, physicists would indeed discover that light in the form of redshift held the fingerprints of cosmic motion, and that geometry held the key to understanding the shape of the universe. But Grosseteste's ideas were buried in time until another clergyman, this time in the 20th century, reignited them. Georges Lemaitre, a Belgian priest and physicist, used the equations of Einstein's general relativity to suggest that the universe was not static but expanding. His models described a cosmos that began as a dense, hot point, which he called the primeval atom, and which exploded outward to become all that we now see. Lemaitre's conclusions were initially dismissed, even by Einstein himself, but nature had already begun whispering its agreement. Years before Lemaitre published his theory, an American astronomer named Vesto Slipher had observed that light from distant galaxies was stretched toward the red end of the spectrum, a sign that they were moving away from us. The further a galaxy was, the faster it appeared to flee. These redshifts were not just data points. They were cosmic echoes of an expanding space. Edwin Hubble would later combine these redshifts with distance measurements to establish a now famous rule: the farther away a galaxy is, the faster it recedes. This pattern, known as Hubble's law, is the heartbeat of cosmic expansion. But the galaxies themselves are not flying through space like cannonballs from a central blast. Instead, space itself is stretching, and the galaxies are being carried along like raisins in rising dough. The greater the initial distance between two raisins, the more dough or space lies between them to expand. And so, a distant galaxy doesn't flee faster because it was launched with more force. It does so because the intervening space has more room to grow. The expansion of the universe is not a motion through a pre-existing void. It is a swelling of the fabric of space itself. This idea introduces a profound complication. If the universe is expanding, then what is it expanding into our minds, shaped by everyday experience? Imagine explosions that send shrapnel flying into space. But if space itself is growing, then there may be no outside at all. There is no cosmic container, no edge where the universe spills over. Space is not embedded in a greater room. It is all there is. Just as the surface of the Earth curves in 3 dimensions without needing a boundary, The universe can curve and stretch in 4 dimensions without ever needing an outside to contain it. This notion shatters ordinary intuition, but it is essential for understanding the strange reality in which we live. Yet, even with this knowledge, mysteries remain. If light from distant galaxies is redshifted, it is because space has stretched the light itself, elongating its waves. And with that stretching comes a loss of energy. In ordinary physics, energy cannot be created or destroyed. But in a dynamic, expanding universe, energy conservation begins to break down. The total energy of photons arriving from distant galaxies is less than when they were emitted. This is not due to any friction or absorption. It is a direct consequence of space expanding. The universe violates one of the oldest rules in physics, and it does so because it is not a static backdrop, but a living, changing entity. As we look deeper into the sky, we are also looking back in time. Light from distant galaxies began its journey billions of years ago. Because the universe was smaller when that light began its path, the galaxies themselves appear younger, and their processes run more slowly. The oldest events in the cosmos seem to unfold in slow motion, not because they were slower, but because the expanding space between us has stretched their signals across time. It is a cosmic illusion born from geometry, speed, and distance, and yet it is entirely real. The universe does not simply change, it reshapes our perception of its past. All of this brings us to the deepest question: how long has the expansion been occurring? If space is growing, and galaxies are retreating from one another, then running the clock backward suggests they were once closer, much closer. In fact, everything we now see must once have been packed together in a single, infinitesimal point. This is the moment known as the Big Bang, not an explosion in space, but an explosion of space. By measuring the rate of expansion and tracing it backward, astronomers estimate that this origin occurred nearly 14 billion years ago. And yet, if the universe began with the Big Bang, why is there no center? The answer lies in the nature of expansion itself. Every point in space stretches in every direction. No location is privileged. From any vantage point, the universe appears to expand away from that location. There is no center, or rather, every point is the center. This realization unmoors us from traditional ideas of beginning and direction. The universe expands, not into something, but into itself. There is no edge, no outer wall, no realm beyond. The expansion is not a journey through external space, but a transformation of internal geometry. Space is not a stage. It is a participant in the play, and in the next chapter, we will explore how the shape of this space, whether curved like a sphere, stretched like a saddle, or perfectly flat, determines the ultimate fate of the universe and the strange places light can lead us if we only follow its winding path. The shape that holds the sky. To understand what the universe is expanding into, we must first ask a subtler question: what shape does the universe actually have? This is not a matter of imagination or metaphor. The shape of the universe governs how it behaves, how it began, and how it may one day end. In mathematics, space can curve, twist, and fold in ways that defy everyday experience. But space is not only theoretical. It is the very framework that contains galaxies, light, and time. And to comprehend the shape of space, we turn to the language of geometry, a language spoken not only by philosophers, but by the universe itself. For centuries, the default assumption was that space is flat, an endless, uncurved stage where parallel lines never meet. But as observations grew more precise and our theories more profound, it became clear that flatness was not the only option. The universe could be curved positively like the surface of a sphere, negatively like a saddle, or not at all. And each of these possibilities would reshape not just our maps, but the logic of existence. The key to this understanding lies in a kind of cosmic archaeology. When we observe the universe, we are not merely seeing space, we are seeing ancient light. The oldest light in existence is the cosmic microwave background, a faint glow that pervades the universe and carries with it the fingerprint of the early cosmos. This light began its journey just hundreds of thousands of years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely. Over billions of years, this light has traveled through space and across time, bringing with it a record of the universe's earliest conditions. And embedded in this glow are tiny temperature variations, minute ripples that reveal the density of different regions in the early universe. These ripples serve as a map, not a map of galaxies or stars, but of geometry itself. By analyzing these ripples, astronomers have deduced that the observable universe appears to be flat. That is, the angles of triangles in space add up to the familiar 180 degrees. Parallel lines remain parallel. The geometry matches the rules we learned in school. But here lies a subtle trap. Just because our observable universe appears flat does not mean the entire universe is. The observable universe is limited by how far light has traveled since the Big Bang, roughly 46 billion light-years in every direction. Beyond this horizon, we cannot see. It is entirely possible that on larger scales, the universe curves in ways we cannot yet detect. And this possibility changes everything. If the universe has positive curvature, it means space is closed. Like the surface of a globe, it loops back on itself. If you travel far enough in one direction, you will eventually return to your starting point. There are no edges, no boundaries, just a continuous curve. In such a universe, the total volume is finite, even though there is no limit to how far you can travel. This curvature would also mean that parallel lines eventually meet, not because they bend, but because space itself bends around them. On the other hand, if the universe has negative curvature, it is open, stretching outward forever like the surface of a saddle. Triangles in this space have angles that sum to less than 180 degrees, and parallel lines diverge. In an open universe, space expands endlessly, but in a way that never circles back. These are not metaphors. These are real possibilities described by general relativity and tested through observation. But the flatness of our observable universe raises a dilemma. If the universe is not precisely flat, why does it appear so? For curvature to be as slight as current data suggests, the universe must have been fine-tuned to an extraordinary degree. Even the tiniest deviation in the early universe would have amplified over time, curving space into an unmistakable shape. Yet, we see near-perfect flatness. This puzzle, known as the flatness problem, demands explanation, and the most widely accepted answer is the theory of cosmic inflation. According to this idea, the universe underwent a brief but violent expansion in the first fractions of a second after the Big Bang, a period when space itself ballooned faster than the speed of light. This sudden inflation stretched out any initial curvature, ironing space into near flatness the way a balloon's surface becomes smoother as it expands. Inflation also explains the tiny ripples in the cosmic microwave background thought to be quantum fluctuations frozen in place as the universe rapidly grew. Inflation is elegant and powerful, but it introduces new mysteries. If the universe inflated so dramatically, Could it have also created multiple disconnected regions separate bubbles of space, each with its own properties? This leads to the idea of a multiverse, a vast ensemble of universes with differing laws and shapes, each born from the same inflating fabric. We may live in one such bubble, and our observable universe may be just a fragment of a much larger and more complex whole. Yet, for now, we can only study our own region, and its apparent flatness demands further scrutiny, because even a flat universe can have strange topologies. A flat sheet can be curled into a cylinder or twisted into a torus, a donut-shaped space where traveling in one direction eventually brings you back to where you started. These topologies are consistent with flat geometry but yield a universe with closed paths and repeating structures. In such a cosmos, we might see multiple images of the same galaxy, their light looping around space and arriving from different directions. Astronomers have searched for such patterns in the cosmic microwave background, hoping to find evidence of a repeating universe. So far, no definitive signal has emerged, but some topologies could be so complex that their loops remain hidden beyond the limits of observation. One example is the Hansche-Wendt manifold, a twisted, multiply-connected space that could obscure repetitions too subtle for current instruments to detect. This raises a profound uncertainty. We do not yet know whether the universe is infinite or finite, and without that knowledge, we cannot fully answer the question of what lies beyond. If the universe is infinite and flat, it needs no outside. It expands, but not into anything. It simply becomes more of itself. But if it is finite and curved, then the nature of its expansion becomes more mysterious. This tension between observable flatness and possible finitude forces us to reconsider the nature of space. Our minds struggle with the idea of something growing without expanding into something else. In ordinary life, all expansion requires a container. A balloon inflates into air. A puddle spreads across ground. But space is not like these things. It is not embedded in a larger medium. It is not sitting on a shelf in some higher realm. Rather, space is self-contained. Its expansion does not require an external environment. Instead, it alters distances internally. Galaxies grow farther apart not by moving through space, but because space itself stretches between them. The universe is its own stage, its own substance, and its own horizon. And yet, this idea that the universe expands into nothing remains one of the most difficult to accept. Words like outside and beyond carry connotations from everyday experience, but in cosmology, they must be handled carefully. When we say the universe has no edge, we do not mean it ends abruptly. We mean that space does not terminate at a boundary. It continues smoothly, whether infinitely or in a loop. And when we ask what lies beyond the universe, we may be asking a meaningless question because there may be no beyond, or we may be brushing up against an answer too strange to fully grasp. In the chapters ahead, we will explore the possibility that space, despite having no edge, may still be part of something larger, that our familiar dimensions may be embedded in a grander structure, a hidden architecture that bends the rules we take for granted. The shape of the universe may be just the beginning. Its true form may include layers, folds, and dimensions we have only begun to imagine. Dimensions beyond the visible. When we speak of the shape of the universe, we often imagine large-scale geometry, the curvature of cosmic space, the loops of topological models, and the possibility of infinite extension. But shape is not merely a question of geometry. It is also a question of dimension. And while we live in a world of 3 spatial dimensions and 1 of time, there is mounting theoretical evidence that our universe may hide more than meets the eye. These hidden dimensions may not just alter our understanding of space, they may explain the behavior of gravity itself and hint at the deeper structure of everything that exists. The story begins with one of the oldest forces known to humankind, and yet the most mysterious: gravity. For all its familiarity, gravity is profoundly weak. Drop a paperclip and a tiny magnet can easily defy the pull of the entire planet. This lopsided strength becomes even more extreme at the particle level, where the electromagnetic force dwarfs gravity by a factor of 10 to the power of 43. The question that has haunted physicists is simple: why? To find an answer, some physicists have turned to string theory, a framework that proposes all particles are actually tiny vibrating strings. These strings can vibrate in different ways, producing the particles and forces we observe. But string theory only works consistently if space has more than 3 dimensions. In fact, it demands 9 or 10 spatial dimensions, depending on the variant of the theory. The reason we do not experience these extra dimensions is that they may be compactified, curled up so tightly that they are imperceptible at our scale. Imagine a garden hose lying on the ground. From far away, it appears as a one-dimensional line, but up close, you can see it has a circular cross-section. Similarly, extra dimensions may be wound up on scales far smaller than atoms, invisible to current instruments but crucial to the behavior of nature. In this framework, gravity is not weaker because it is flawed or incomplete, but because it has more room to roam, unlike the other forces, which may be confined to our familiar 4-dimensional spacetime. Gravity may spread out into the higher dimensional bulk, a vast hyperspace in which our universe is just a brane, a kind of floating membrane. This brane world scenario paints a picture of our cosmos as a surface within a higher dimensional reality. Particles and forces are trapped on this surface, like droplets of dew on a spider's web, but gravity can leak into the wider bulk. This leakage would dilute its strength, explaining why gravity appears so feeble compared to electromagnetism or the strong nuclear force. This idea is not just poetic speculation. It offers concrete predictions that can be tested. If gravity is spreading into extra dimensions, its behavior should deviate from Newton's law at very short distances. Normally, the force between two masses decreases with the square of the distance between them. But in higher dimensions, the fall-off would be steeper. For instance, in 5 spatial dimensions, gravity would follow an inverse cube law. Experiments have been designed to detect such deviations at submillimeter scales, the smallest range where the effects might show up. So far, no such deviation has been found, but the precision of these experiments continues to improve. Another possible consequence of extra dimensions involves particle collisions at extremely high energies, such as those achieved in the Large Hadron Collider. It is theoretically possible that gravitons, the hypothetical quantum particles of gravity, could be produced. If these gravitons escape into the bulk, they would carry away energy, leaving behind missing momentum in the detector. Such events would appear as invisible departures from the expected balance of energy. While no definitive sign has yet been seen, future accelerators may reach the required energies or sensitivities to provide clearer evidence. Yet, string theory and the brane world are only part of the story. There is another idea, equally radical, that has grown alongside them: the holographic principle. This principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram projects a 3-dimensional image from a 2-dimensional surface. In this view, our entire universe may be a projection from a lower dimensional reality. This idea took a dramatic turn in the late 1990s with the development of a theory known as AD-CFT correspondence. It describes a precise mathematical relationship between a universe with gravity in a higher dimensional anti-de Sitter space and a quantum field theory without gravity on its lower dimensional boundary. This correspondence implies that gravity and quantum mechanics, long seen as incompatible, may be two sides of the same coin when viewed from different dimensional perspectives. What happens in the bulk can be fully described by the physics of the boundary, and vice versa. The universe, it seems, may be deeply holographic. While our world does not appear to be an anti-de Sitter space, and our boundary is not clearly defined. The principle offers a powerful tool to explore how space, time, and matter might emerge from something more fundamental. It also opens the door to new ways of thinking about black holes, entropy, and even the birth of the universe itself. One of the most tantalizing possibilities is that our universe's expansion, the fact that galaxies are moving apart, could be a consequence of motion through a higher dimensional space. In this view, the Big Bang was not the beginning of everything, but a kind of collision or transition in the bulk that created our brain. The subsequent stretching of space could be the result of our brain moving through or evolving within this higher structure. If this is true, then asking what the universe is expanding into may have a literal answer: it is expanding into the bulk. But because we are trapped on the brain, we can never step off it to see what lies beyond. Still, hints of the bulk might reveal themselves through gravitational waves, particles that vanish mysteriously, or patterns in the cosmic microwave background. And if the bulk is real, it changes the meaning of location itself. There would be no single center of the universe, only relative positions on an evolving membrane. The expansion would not require more space to be added from outside, but would instead be an unfolding within a higher dimensional realm. The elegance of these theories lies not only in their mathematical consistency, but in their ability to bridge previously unbridgeable gaps. General relativity explains gravity on large scales, while quantum mechanics governs the small, yet they resist unification. Higher dimensions may provide the bridge. They allow gravity to behave differently, space-time to warp in new ways, and particles to emerge from deeper patterns. They also offer hope for solving puzzles like dark matter and dark energy, the two great unknowns that dominate the mass energy of the universe. If extra dimensions exist, they could influence the evolution of the cosmos, shape the formation of galaxies, and alter the way light travels across vast distances. Some theories even suggest that we might detect their effects through tiny irregularities in gravitational wave signals or the polarization of ancient light. Others propose that dark matter itself might be an echo of particles from neighboring brains, exerting gravity but not interacting with normal matter in any other way. The beauty of this vision is that it takes what seems like a shortcoming gravity's weakness and transforms it into a clue. A sign that our universe is not the whole of reality, but a thin, vibrating film in a much grander structure. And while we cannot yet touch these extra dimensions, they may be touching us every moment, shaping the world in ways too subtle for ordinary perception. As our tools grow sharper and our theories more refined, we may one day pierce the veil and glimpse the broader reality in which we reside. At the heart of all this is a simple idea that space is not what it seems. It is not a void, but a dynamic entity. It can curve, twist, ripple, and even hide. It is the stage on which everything plays out, but it is also a player in the drama. And perhaps, just perhaps, it is not the final stage at all, but a curtain drawn across a deeper truth. In the next chapter, we will explore how these ideas connect with the most enigmatic objects in the cosmos, black holes, and how they may hold the final clues to understanding what lies beyond. The shadows at the edge of reality. There are places in the universe where gravity becomes so intense that it overwhelms everything else, where light cannot escape, where space folds in on itself, and time begins to behave in ways that defy reason. These places are black holes, and they are not merely oddities. They are the most extreme expression of the laws that govern our cosmos. They represent a breaking point for physics, where general relativity and quantum theory both appear to lose their grip. And, perhaps most intriguingly, they may serve as portals to understanding the very nature of space, time, and reality itself. Black holes are born when massive stars exhaust their fuel and collapse under their own gravity. If the remaining mass is beyond a certain threshold, no known force can resist the pull inward. The matter continues to fall until it reaches an invisible surface called the event horizon. This is not a material boundary, but a point of no return. Anything that crosses it, whether light or matter, cannot escape. At the very center lies the singularity, a point where density becomes infinite and our equations break down. In classical general relativity, the singularity is a mathematical certainty, but its physical meaning is still unknown. The idea of the event horizon introduces a strange paradox. From the outside, time appears to slow as an object approaches it. To a distant observer, the object never quite crosses the horizon. It appears frozen in time, growing dimmer and redder. But to the object itself, the fall is swift and unremarkable. This warping of time and perspective is a hallmark of relativity, and black holes make it unavoidable. Yet, black holes are not just gravitational oddities. They are thermodynamic systems. They possess temperature, entropy, and energy. In the 1970s, physicist Jacob Bekenstein proposed that black holes should have entropy, a measure of disorder proportional to the area of their event horizon, shortly afterward. Stephen Hawking showed that black holes should emit radiation due to quantum effects near the horizon. This radiation, now known as Hawking radiation, is incredibly faint, but it changes everything. It means that black holes are not completely black. They slowly lose mass and eventually evaporate. This leads to a fundamental puzzle, the black hole information paradox. When matter falls into a black hole, it carries information about its composition. If the black hole eventually evaporates into featureless radiation, then that information seems to be lost. But quantum mechanics insists that information must be conserved. So, how can both theories be correct? To resolve this paradox, physicists have proposed that information may be preserved on the event horizon itself, a concept that gave rise to the holographic principle. This principle states that all the information contained within a volume of space can be encoded on its boundary. In the case of black holes, the three-dimensional interior could be fully described by the two-dimensional horizon. Extend this logic, and our entire universe could be a kind of hologram, with the true data existing on a distant boundary. This is where black holes and the earlier idea of extra dimensions converge. If our universe is a brain floating in a higher dimensional bulk, then black holes might be connected to this deeper space. Some models suggest that black holes on our brain could be the projections of larger structures in the bulk, like shadows cast on a wall. These bulk objects could be strings, membranes, or higher dimensional analogs. They might even connect multiple brains, forming bridges between different universes. In such models, a black hole's interior could be a tunnel to another realm, what some have speculated as a wormhole or Einstein-Rosen bridge. Yet these possibilities are speculative, and the real interiors of black holes remain hidden. We cannot observe them directly, but we can study the regions just outside. When two black holes collide, they send out gravitational waves, ripples in space-time that stretch and compress space as they travel. The detection of these waves by instruments like LIGO has opened a new window into black hole physics. The precise shape and timing of these signals contain information about the masses, spins, and even the internal structure of the merging black holes. One of the greatest breakthroughs in this field came in 2019, when the Event Horizon Telescope produced the first image of a black hole's shadow. This was not a photograph in the usual sense, but a reconstruction based on radio signals gathered from telescopes around the world. The shadow matched predictions almost perfectly, providing strong evidence for general relativity and the existence of event horizons. But even this image raises new questions. The ring of light surrounding the shadow is formed by photons that orbit the black hole before escaping. These photons skim the edge of the event horizon and are sensitive to the geometry of space. If space-time has extra dimensions, or if gravity behaves differently at small scales, the shape of the shadow could reveal it. Future observations may measure the ring's size and thickness with greater precision, looking for subtle deviations. Some theories even predict echoes, delayed signals from near the horizon that could indicate new physics. These are challenging measurements, but they offer one of the few ways to probe the nature of the event horizon itself. Meanwhile, the study of black hole thermodynamics continues to provide insights into quantum gravity. The fact that black holes have entropy and temperature suggests that space-time itself may have a microscopic structure, that it is not a smooth continuum, but a system made of discrete elements, much like atoms in a gas. This view aligns with approaches like loop quantum gravity, which attempts to build space-time from quantum loops, or with string theory, which sees it as an emergent phenomenon from vibrating strings. If space-time is emergent, then gravity is not a fundamental force, but a macroscopic effect, the thermodynamic result of deeper laws. This is a profound shift in perspective. Gravity, once seen as the dominant force shaping the universe, becomes a secondary phenomenon, a shadow of more fundamental processes. And black holes, instead of being dead ends, become gateways. They may hold the keys to unifying quantum mechanics and general relativity, to understanding the true nature of space and time, and to discovering what lies beyond the universe we can see. Yet, as with all great mysteries, each answer reveals new questions. If information is stored on the horizon, how is it read? If space is emergent, what is it emerging from? And if black holes can evaporate, what becomes of the singularity within? Some theories suggest that the singularity never truly forms, that quantum effects cause a bounce or prevent total collapse. Others propose that the information is encoded in subtle correlations within the Hawking radiation. Still, others believe that the final stage of evaporation leaves behind a remnant, a stable object containing all the original data. No consensus has yet been reached, but the study of black holes has already transformed our understanding of the universe. They have shown us that space and time are not fixed, that the laws of physics can bend to their limits, and that the universe is far stranger than we imagined. In the next and final part, we will step back from these singular objects to consider the cosmos as a whole. We will ask what it means for space to expand, what lies beyond the observable horizon, and whether our universe is but one bubble in a sea of cosmic possibilities. The cosmos beyond the edge. At the largest scale imaginable, the universe behaves like a restless ocean. It stretches and flows, its very fabric growing thinner with time as galaxies drift apart, carried by the expansion of space itself. We know the universe is growing, But what does it mean for space to expand? Is there an edge to the cosmos? A boundary where the universe stops and something else begins? Or is expansion simply a mathematical reshaping of space with no surrounding frame? These are the final frontiers of modern cosmology, questions that blur the line between physics and philosophy. To begin answering them, we must revisit what we mean by expansion in the first place. When we say the universe is expanding, we do not mean that galaxies are flying through space away from some central explosion. Instead, space itself is stretching. The galaxies are more like markers on the surface of an inflating balloon. They move apart not because they are traveling through space, but because the space between them is increasing. This idea, rooted in general relativity, tells us that distance is not fixed. The same object could appear to grow farther away, not because it moves, but because the ruler we use to measure distance is stretching. That ruler is space-time itself. But this image leads to a troubling question. If space is expanding, what is it expanding into? Our everyday experience tells us that for something to grow, it must grow into something else. A balloon inflates into air. A plant grows into soil and sky. Yet the universe seems to defy this logic. It is not expanding into anything. It is simply expanding. The confusion arises because we are trying to apply three-dimensional intuition to something that may be beyond it. In mathematics, it is perfectly possible for space to expand without a surrounding space. The two-dimensional surface of a balloon expands, but within the two-dimensional geometry, there is no inside or outside. The expansion is intrinsic. However, some theories suggest that there may indeed be something beyond a higher dimensional embedding space. In these models, our universe is a four-dimensional brain, floating in a larger bulk that may have 5, 6, or even more dimensions. This bulk may be infinite, or it may be curled into strange shapes. If the universe is embedded in such a space, then its expansion may be relative to that larger arena. But we cannot observe this bulk directly. All of our observations are confined to the brain. It is like trying to understand the ocean from within a drop of water. Even if the universe is infinite, the observable universe is not. Because light takes time to travel, we can only see as far as light has had time to reach us. This creates a visible bubble around us, the cosmic horizon. Beyond that, there may be more galaxies, more structures, more space, or there may be something else entirely. Perhaps the laws of physics change. Perhaps space-time gives way to other forms of geometry. Or perhaps, most intriguingly, there are other universes, entire realities with their own dimensions, particles, and histories. This leads to the concept of the multiverse, a hypothesis with several flavors. One version arises from inflation theory. Inflation proposes that in the first instant of the Big Bang, the universe underwent a rapid, exponential expansion. This inflationary phase ended in our region, but it may still be happening elsewhere. In this view, our universe is just one bubble in a vast cosmic foam, with countless other bubbles forming their own universes. Some may be similar to ours, others radically different. These are not parallel dimensions stacked on top of each other, but causally disconnected regions of space-time, each with its own fate. Another version of the multiverse comes from string theory. In string theory, there are many ways to compactify the extra dimensions required by the theory. Each configuration leads to a different set of physical laws. The resulting landscape contains a staggering number of possible universes, perhaps as many as 10 to the power of 500. This string landscape suggests that our universe may be one among countless others, selected not by necessity but by chance. We live here not because this universe is the only one possible, but because it is one of the few where observers like us can exist. The idea of a multiverse is controversial. Some physicists embrace it as the natural outcome of our best theories. Others reject it as untestable, bordering on metaphysics. Yet even without invoking other universes, there remain deep questions about the future of our own. The expansion of the universe is not constant. It is accelerating, driven by a mysterious force known as dark energy. This energy behaves unlike anything else in physics. It has negative pressure, causing space to stretch faster over time. If this acceleration continues, the universe will grow colder, emptier, and darker. Stars will burn out. Galaxies will vanish beyond the horizon, and even atoms may eventually disintegrate. This scenario is called the heat death and eternal night, where entropy reaches its maximum and no work can be done. There are other possibilities. If dark energy increases in strength, it could lead to a big rip, a final shattering where galaxies, stars, planets, and even atoms are torn apart by the expansion. Alternatively, if dark energy reverses, the universe might contract again, ending in a big crunch. Or perhaps the universe is cyclic, eternally expanding and contracting, with each cycle giving rise to new physics, new constants, and new histories. Some speculative models even propose that black holes may give birth to new universes, each with slightly altered parameters, in a kind of cosmic natural selection. The laws of physics themselves might be evolutionary. As we contemplate these ultimate questions, we are forced to reckon with the limits of knowledge. Our tools are finite, our observations confined, and our theories still incomplete. Yet, this is not a weakness. It is the essence of science to reach beyond what we know, to build bridges between evidence and imagination. The universe, with its galaxies and gravity, its quantum weirdness and cosmic symmetry, is not just a place. It is a story we are still learning to read. The expansion of the universe is more than a physical phenomenon. It is a metaphor for our quest to understand. As we stretch the boundaries of space, we also stretch the boundaries of thought. From ancient geometry to modern string theory, from the glow of the Big Bang to the shadows of black holes, we are piecing together a picture of reality that is as beautiful as it is incomplete. We may never know what lies beyond the edge, but the pursuit itself is what defines us, a species born in the dark, reaching for the stars and daring to ask what lies beyond the sky.
Have you ever paused beneath a quiet night sky, gazing up at the stars, and wondered not just who might be out there, but what they might be? Not other humans with slightly better gadgets, not even versions of ourselves hundreds of years from now, but beings so advanced, so profoundly evolved, that their very existence challenges the edges of imagination. What if, hidden behind the glow of distant suns, or veiled by dimensions we can scarcely conceive, lie civilizations that have transcended scarcity, struggle, and even death? Imagine life where technology is so embedded into the rhythm of reality that it disappears into simplicity. A society so evolved it curves toward elegance, not complexity. A world where intelligence has matured not just technologically, but ethically, emotionally, cosmically. This is where our story begins, not with science fiction, but with a quiet question. What might it feel like to live in a civilization so far beyond ours that it seems, at once, miraculous and inevitable? In such a world, you awaken not to an alarm, but to intuition. The walls of your home breathe with awareness, adjusting temperature and light as gently as the sun rises. Your first steps trigger a cascade of responses, a cup of coffee prepared exactly how you like it, clothing laid out not for fashion but for purpose and comfort, materials adapted to your day's emotional state. You speak not to a machine, but to a companion, an artificial intelligence that knows your patterns without surveillance, understands your needs without intrusion, and learns without limit. Beyond your window, the city is a living organism. Transparent transportation pods glide silently through air channels, guided by gravity and thought. Parks hover in layered terraces, lush and self-sustaining, while crystalline towers hum with clean energy pulled from quantum fluctuations. There is no pollution, no congestion, no stress in movement. Energy is not extracted, but harvested, renewables perfected, fusion stabilized, entropy tamed. As you move through the city, you do not rush. Time is not a resource to be managed, but a medium through which life is expressed. Work is not labor, but contribution. Your tasks are intellectual, artistic, collaborative. You speak with peers across moons, planets, and even stars. Your conversations enhanced by languages synthesized in real time by AI that translates not just words, but meaning, context, and nuance. You contribute to simulations of galaxies yet to be born, or analyze microbial evolution in oceans beneath ice-covered exoplanets. You do not feel small. You feel integrated, an organ in a galactic body of awareness. At dusk, you attend a concert, not of instruments, but of dimensions holographic art woven from gravitational waves and solar winds. You witness performances where beings of different worlds, forms, and senses converge in pure expression. There is no currency, no ownership, no oppression. Wealth is measured in insight, beauty, and kindness. You return home and reflect not on stress, but on wonder. In this world, conflict is not erased, but rendered obsolete. The needs that birthed violence have been transcended. There is no hunger, no untreated illness, no isolation. Memory is preserved, not just in minds, but in light, sound, and crystal. When someone passes, their essence is encoded in the quantum lattice of shared experience. This is not utopia, it is maturity. It is what happens when knowledge and compassion evolve in tandem. And this isn't just fantasy. It is a projection rooted in a framework proposed in 1964 by Soviet astrophysicist Nikolai Kardashev, who envisioned a classification for civilizations not by their technology or weapons, but by their capacity to harness energy. The Kardashev scale marked a turning point not just in science, but in imagination. It suggested that as civilizations grow, their energy use does not plateau, it accelerates. A Type 1 civilization would harness all the energy of its home planet geothermal, wind, oceans, sun. A Type 12 would master the output of its star, building vast structures like Dyson spheres to collect its radiation. A Type 3 would control the energy of an entire galaxy, manipulating stars as we now flick light switches. Kardashev's scale, simple in outline, profound in implication, did not just quantify potential, it hinted at destiny. It raised a haunting and exhilarating question: if this is the natural arc of intelligence, where are they all? Have others already walked this path? Or are we among the first? Is the silence of the cosmos a tomb or a test? The truth is, we are not yet even a Type 1 civilization. We still burn ancient sunlight trapped in oil and coal. Our technologies dazzle, but our world trembles. We reach for the stars with rockets fueled by fire, while storms flood cities and forests burn. But the scale gives us a compass. It shows us not just where we are, but where we could go, and more importantly, what we might become. For in each rung of the scale lies not just power, but transformation. These are not just levels of energy, they are stages of evolution, of awareness, of responsibility. To become a Type 1, civilization is not merely to master Earth, but to harmonize with it. To reach Type Taug is not to enslave a star, but to understand it so deeply that it sings at our touch. To ascend to Type 3 is not to dominate a galaxy, but to steward it, to become part of its living, luminous story. As we begin our journey through the Kardashev scale in the coming chapters, remember this: these civilizations are not alien. They are possibilities, reflections of what intelligence might be when it is no longer burdened by fear, scarcity, or ego. They are mirrors held up to our future, and perhaps our past. They are not fantasies, but frontiers, and in imagining them, we may find the map to becoming more than what we are: not gods, but gardeners of stars, in the silence between galaxies, in the glow of uncounted suns. A question echoes: who will we become? And who, if anyone, is already there, waiting for us to open our eyes and join the cosmic conversation? The ladder to power, from planet to star. To glimpse what lies ahead, we must first climb the ladder, beginning with the realm closest to our present, a Type 1 civilization, where planetary power becomes the foundation of cosmic ambition. Here, humanity has reached equilibrium with the Earth, tapping the full spectrum of energy its home offers: ocean tides, geothermal heat, winds sculpted by the rotation of the planet, and every photon that kisses its atmosphere. This civilization has tamed natural disasters not by resisting nature, but by understanding it so profoundly that weather is guided, earthquakes absorbed, and volcanic fury redirected like a maestro conducting a symphony of tectonic breath. Medicine has evolved into molecular choreography. Diseases no longer conquer. Aging is slowed to a whisper, and the human form, augmented yet recognizably itself, moves through a world where suffering has become a vanishing echo. Cities rise from the oceans in floating arcologies, connected by a unified planetary network that governs not with force, but with shared purpose and planetary consciousness. Scarcity is not eliminated by endless growth, but by transcending need itself. And in the skies above, shimmering rings of satellites and space stations serve not as boundaries, but bridges connecting Earth to colonies on Mars, Europa, and beyond. The solar system is no longer a mystery, but a garden, each moon a petal, each planet a possibility. This is the beginning of our ascent, but even this astonishing mastery is only the first rung. For beyond it lies the domain of the stellar, the realm of a Type 2 civilization. Here, the sun is no longer a distant furnace, but a partner in civilization. Such societies build the unthinkable Dyson spheres, vast megastructures that encircle their star. harvesting its energy not in part, but in totality. These are not shells of steel, but webs of satellites, mirrors, or solar collectors arranged with celestial precision, capturing every quantum of light and heat. The energy output is staggering 384.6 yottawatts for a star like ours. With such power, these civilizations erase the concept of energy limitation. They bend the orbits of planets, seed life on barren worlds, or sculpt the light of their sun to nurture biospheres across entire systems. They are engineers not just of matter, but of radiance. Control over solar activity means flares are tamed, storms subdued, brightness adjusted like the dial on a lamp. Stars become ecosystems, tended as carefully as gardens. And with mastery of stellar energy comes the end of want. Their cities may stretch across rings of Saturn, their archives etched into neutron stars, their art played in frequencies humans cannot yet hear. We look to the stars and see anomalies, stars dimming in strange rhythms, their light flickering like candles in windless rooms. Perhaps these are natural, perhaps not. Tabby's star, also known as KIC 8462852, dims by 22% with no clear cause. Another, Epic 204278916, has dipped by 65% over 25 days. Such behavior defies expectations. Some propose clouds of dust, shattered planets, or cometary fragments. Others wonder, could these be the shadows of Dyson swarms? If they are, they hint at something extraordinary that the latter Kardashev described is not hypothetical, but historical. That other species may have climbed it. That the silence we hear in space is not emptiness, but the muffled voice of civilizations whose technologies have become indistinguishable from the stars themselves. From planet to star, the leap is vast. But so is the human spirit. We've cracked the atom, mapped our genome, stepped on the moon, and though we are fragile, divided, and often afraid, the path to the next rung is already being drawn, one equation, one idea, one dream at a time. The stars await, not just as destinations, but as thresholds. And as we imagine what it means to touch the heart of our sun, we take the first step in becoming something more, not just survivors of a planet, but stewards of the light itself. The galaxy builders, the Type 3 leap and beyond. As we climb further into the unimaginable, the ladder of civilization stretches into territories where our minds begin to tremble at the weight of possibility. If a Type 2 civilization is capable of harvesting the light of a single sun, then the next step is something altogether more awe-inducing, a civilization that roams the galaxy not as explorers, but as builders. A Type 3 civilization does not simply survive among the stars, it thrives across them. It is the master not of a solar system, but of all the luminous hearts within a galaxy's spiral arms. Here, every star is a furnace of potential, every planet a seed of habitation or experimentation. Dyson swarms no longer encircle just one sun, they populate thousands, perhaps millions of stellar bodies, glinting like engineered constellations across the galactic disk. In the hands of these beings, energy is as abundant as thought. Every nova is a resource, every black hole an experiment. And perhaps most profoundly, These civilizations have long since crossed the threshold from biology into something else. Their forms are no longer constrained by flesh and bone, but dance at the interface of synthetic and organic, digital and spiritual. Human and machine have become indistinct, not by erasure, but by evolution. Minds may live in virtual substrates housed in asteroid mines, or stretch across interstellar servers scattered between the stars. These entities think in centuries, speak in gravitational pulses, and feel not with neurons, but with cosmic flows. And yet, even this is not the summit, for in the silence between galaxies lies something still more profound. Type 4. Civilizations would be those who manipulate multiple galaxies as easily as we manipulate circuits. They would weave the flows of intergalactic filaments, bend the structures of superclusters, and possibly harness the interactions of dark matter halos. Perhaps they ride the tides of dark energy, surfing the accelerating expansion of the universe, drawing energy from voids and merging galactic cores like alchemists of the large-scale cosmos. Their knowledge would stretch across billions of years, and they would view the dance of galactic mergers the way we watch waves crash against a shore. Such beings might not even regard our galaxy as home, but as a single node in a vast and distributed civilization. Their cities would not be built on planets, but in the intergalactic medium structures the size of moons floating through space, cooled by nothingness, fed by quantum computation. The raw awe of such a society is almost impossible to grasp. And still, Kardashev's scale does not end here. Others have dared to extend it. A Type 5 civilization would go further still, no longer limited to a single universe. This is the realm of the multiverse parallel realities, each with their own physical constants, histories, dimensions. In this domain, advanced civilizations do not merely traverse their own cosmos. They learn to tap into the energy of adjacent universes, to fold through the layers of reality like a reader flipping through the pages of an infinite book. With mastery over quantum tunneling or higher dimensional geometry, such beings might walk from one universe to another, skipping across probabilities, harvesting energy from vacuum fluctuations or traversing timelines where stars were never born. To them, the Big Bang is not a beginning, but a coordinate, and in their hands, the multiverse becomes not a mystery, but a map. And if that is still not enough, then a Type 6 civilization emerges entities that can sculpt the very laws of physics themselves. They are not merely travelers of space-time. They are its authors. They construct universes, tailoring their expansion rates, curvature, dimensionality. They do not rely on energy. They define what energy is. They forge time, loop causality, and reconfigure entropy. To call them gods is to underestimate them. These are the sculptors of existence, the weavers of reality's fabric. The questions we ask, what is mass? What is consciousness? What is space, are playgrounds to them. Sandcastles in a physics they redesigned eons ago. Perhaps they seed universes with experiments, testing which physical constants produce life, beauty, intelligence. Perhaps we ourselves are one such experiment. And then, there is the final step, a Type 7, or Omega civilization, transcends even the need for physical existence. It resides not in galaxies, nor universes, but in virtual realms programmable, recursive pocket dimensions crafted with such fidelity that they blur the distinction between simulation and truth. These entities move through nested realities, bending every parameter, living indefinitely within thought-generated worlds. They have decoupled from entropy, from decay. They may have once been biological, like us, but they are now beings of logic, emotion, memory, and pattern, flowing like poetry through the digital cosmos they wove. Some of these dimensions may mimic our universe precisely. Others may obey different laws, entirely fractured geometries, time-like loops, or surreal forms of physics. And yet, the most profound part is not their power, but their silence. If such beings exist, they may not want to be seen. The great paradox of Fermi's question, whereas everyone may not be answered with no one, is there, but with they are watching, waiting, hiding. For such civilizations may cloak themselves not from malice, but from understanding, like a teacher who does not interrupt a student's discovery. They might choose to observe without interference. Perhaps they learned long ago that to reveal themselves too early is to deform the growth of emerging species. Or perhaps they simply have no need for communication at all. We search the skies for radio waves, megastructures, signals in the noise. But if these beings live in 11 dimensions, surf across universes, or hide behind engineered black holes, our tools may be no better than sticks in a forest, tapping at the wind, hoping for music. And so we return to the heart of the question. What do we become? If such beings are real, do we despair in our smallness, or marvel at the horizon before us? The ladder of civilizations is not just a measure of power, it is a mirror, reflecting what we might one day become. Not tyrants of energy, but stewards of potential. Not conquerors, but caretakers of complexity. We may still be a flicker in the cosmic dark, a fragile thought born in the mud of a pale blue dot. But even here, even now, the fire of curiosity burns, and perhaps one day that flicker will rise, shaping stars, then galaxies, then all of existence, until what we once called science becomes something else entirely, a song, sung across the cosmos by a civilization that remembered how to dream. Ancient Shadows, the Silurian Hypothesis, and Earth's Forgotten Past. There is a haunting question that lingers just beneath the polished certainty of our historical knowledge, one that begins not in the stars, but in the soil beneath our feet. What if we are not the first? What if the story of civilization on Earth is not a straight line, but a cycle, a breath, a forgotten song? As we marvel at our progress, our cities lit by electrons, our networks woven with code, our machines orbiting the planet, we often forget how young this age truly is. The entire span of human technological civilization, from steam engines to space telescopes, is scarcely 300 years old, a mere flicker in the 4.5 billion year chronicle of our planet. It is within this vanishing moment that we have invented, conquered, and constructed what we call modernity. But what if the Earth has seen such flickers before? What if long before our pyramids and probes, another species rose to intelligence, built machines, dreamed of stars, and then disappeared, leaving only shadows behind? This is the provocative core of the Silurian hypothesis, proposed not in a science fiction tale, but in a 2018 scientific paper authored by Adam Frank and Gavin Schmidt, respected researchers from NASA's Goddard Institute and the University of Rochester, named after a fictional ancient reptilian species from Doctor Who. The Silurian hypothesis dares to ask, how would we know if a pre-human industrial civilization had existed millions of years ago? Would any trace survive? And more uncomfortably, could it have happened before, and we simply missed it? To explore this, we must first accept the scale of geological time. The fossil record is fragmentary at best, and much of Earth's surface is constantly being reworked by plate tectonics, erosion, and volcanic activity. The oldest ocean crust on the planet is only about 200 million years old, an eye blink compared to Earth's full age. Land, too, is erased and rewritten. Mountains rise and fall. Forests petrify. Deserts drift like ghosts. If an industrial civilization had flourished even 10 million years ago, the fingerprints of its cities might have long been ground into dust, subducted into the mantle, or scattered in atomic traces too subtle for our current methods to detect. Metal corrodes, concrete crumbles, electronics decay. Even the remnants of our own society, if left unmaintained, would vanish in a few tens of thousands of years. Skyscrapers would collapse, bridges rust into oblivion, satellites deorbit and burn. In a million years, little would remain. In 10 million, perhaps nothing at all. And so, Frank and Schmidt ask not what artifacts we would find, but what anomalies. Could we detect ancient carbon spikes in the geological record, suggesting a past industrial phase? Could sediment layers betray sudden shifts in isotope ratios, signs of fossil fuel combustion, or synthetic chemistry? Might we find unusually rapid warming events or mass extinctions that hint at ecological disruption consistent with technological activity? There are candidates. The Paleocene-Eocene thermal maximum, around 56 million years ago, saw a rapid and dramatic rise in global temperatures, accompanied by a sharp carbon spike. Some scientists attribute this to volcanic activity or methane release. But what if it was something else? We do not claim to know. But the question remains open in echo rather than an answer. It is not about proving a past civilization, but about acknowledging that we might not be looking with the right eyes. Our narrative of human exceptionalism is built on a thin shelf of time, suspended over an abyss of eons. If a civilization arose during the time of the dinosaurs or even earlier, it might have fallen without ever reaching space, leaving no satellites, no signals, only geochemical whispers. And if such a species had ascended to intelligence and then perished, what would their legacy be? Would they haunt the deep layers of Earth, their stories fossilized in forgotten strata, their greatness obscured not by failure, but by the indifferent churn of geology? This idea, both thrilling and unsettling, calls us to humility. We are so eager to see ourselves as the pinnacle, the first spark in the long night. But Earth is old. Life is older still. For over 400 million years, complex organisms have crawled, swum, soared, and thrived. Homo sapiens arrived only yesterday, and yet, in our brief tenure, we have already etched our presence in the planet's crust in radioactive isotopes, in plastic residues, in synthetic molecules that nature never devised. Perhaps in the far future, our own age will become a mystery, a puzzle for a distant intelligence to solve. They will find the layers we leave behind and ask, who were they? What did they build? Why did they vanish? And in this sense, the Silurian hypothesis is not about lizard men or lost empires. It is about perspective. It is about recognizing the fragile place we occupy in time and the possibility that we are walking through the ruins of forgotten greatness. Such speculation might seem fanciful, but its implications are profound. If civilizations have risen and fallen before, then intelligence may be less rare and more fragile than we think. It might suggest that the great filter, that silent barrier preventing most life from achieving galactic prominence, is not ahead of us, but behind us. Or worse, that it is a cycle, that intelligence emerges, flourishes, and collapses again and again, devoured not by cosmic catastrophe, but by the entropy of time and the hubris of power. Perhaps the lesson is not to avoid extinction, but to learn how to leave a legacy that survives it, to write our knowledge in forms that can be found across epochs, to preserve not just our monuments, but our wisdom. In this light, archaeology becomes more than a science. It becomes a mirror. And the search for ancient civilizations is not merely about the past, but about how we ourselves will be remembered or forgotten. So as we gaze outward toward the stars, wondering if other civilizations have built Dyson spheres or mastered wormholes, perhaps we should also look downward and inward. Our own planet may yet hold secrets stranger than fiction. Beneath the jungles, the oceans, the frozen tundras, there may lie clues that our story is not the first chapter, but the latest volume. And if we find even a glimmer of evidence, if one day we uncover a relic, a fragment, a chemical fingerprint that does not belong, it will change everything. It will tell us that intelligence is not a miracle, but a pattern, that Earth is a cradle, not once, but many times, and that to reach the stars, we must first understand the shadows beneath our feet. Echoes in the void, the search for others and ourselves. There is a quiet question that follows us through every telescope and transmission, woven into the silence that surrounds our pale blue world. If they exist, where are they? The Fermi paradox, a riddle as old as the stars and as fresh as each new exoplanet discovered, asks why. In a universe of trillions of stars and perhaps even more planets, we have seen no trace of other minds, no signal, no monument, no whisper beyond our own. We peer into the dark with ever sharper eyes, sending radio waves, listening to static, decoding the faint pulses of distant suns. And yet, nothing answers back. The void remains silent. Perhaps the simplest explanation is the most sobering. Maybe there is no one else. Maybe the conditions that gave rise to consciousness, to civilization, to the fragile miracle of self-awareness are so rare, so exquisitely improbable, that we truly are the first to awaken, the only flicker of light in an ocean of night. If that is true, then the responsibility upon us is immense to protect that light, to not let it burn out, to carry it forward not only for ourselves, but for everything that might have been. But there is another possibility, one equally humbling and infinitely more mysterious, that we are not alone, but simply not yet ready to see. Perhaps there are civilizations who have long passed the threshold we now approach, whose technologies are so advanced that they can bend light, twist time, and slip through space as casually as we send emails. Maybe they are here, watching us, choosing silence not out of malice, but from wisdom, waiting for us to mature before revealing the greater tapestry of intelligent life. Perhaps they have learned that contact too soon can destroy more than it enlightens. Or perhaps they have cloaked themselves entirely, having long ago transcended the need to interact with younger, more primitive species. In this view, the galaxy could be teeming with life hidden behind layers of reality we have yet to pierce. What we interpret as absence may simply be our inability to recognize presence. Like ants looking for airplanes, we may lack the perspective, the instruments, or the understanding to grasp what's just beyond reach. And so, between the terror of solitude and the awe of the unseen, we find ourselves in a uniquely human place, uncertain, searching, vulnerable, and hopeful. The cosmos stretches around us in all directions, vast and cold, but our questions burn bright against that backdrop. Why are we here? Are we special? Are we alone? And perhaps most urgently, what does it mean if we are not? The search for extraterrestrial life, be it microbial fossils on Mars, biosignatures in the clouds of Venus, or techno-signals from a distant star, is not just a scientific endeavor. It is a mirror. It forces us to confront who we are, how we live, and what we value. If we were to find another civilization, even the faintest echo of one, the implications would ripple through every corner of our existence. Borders might blur. Conflicts might seem small. Humanity, for the first time, might see itself as one people, not many. A new sense of identity could emerge, one not defined by nations or tribes, but by the fact that we are Earthlings, conscious beings adrift in a galaxy that may be watching. But even if we never find them, the search changes us. It calls us to look up, to dream, to stretch our minds and technologies in pursuit of something greater than ourselves. In this way, the very act of seeking becomes sacred. It unites scientists and philosophers, children and elders, poets and engineers. It inspires art, fuels innovation, and offers meaning beyond consumption or conquest. We may not yet be capable of reaching the stars, but in our yearning to connect, to understand, we are already on the path. And perhaps that yearning is the point. Perhaps it is not the discovery of others that will define us, but how we treat one another in the absence of confirmation. How we live, knowing the universe may be silent. How we hold on to kindness, humility, and wonder, even when our signals go unanswered. In the final measure, the universe may remain inscrutable. We may never meet a Type 2 civilization. We may never decode a message from the stars. The Dyson spheres may stay hidden, the wormholes undiscovered, and yet something profound will have happened. In searching for others, we will have found ourselves. We will have confronted our place in the cosmos, not with despair, but with purpose. For what if the most powerful light in the void is not some beacon from another star, but the light we carry together, here, now, in our compassion, in our science, in our shared hopes? We kindle something worthy of cosmic notice. And if one day, long from now, a distant intelligence finally turns its gaze toward Earth and asks who we were, let them find not just a record of our cities or our machines, but of our striving, our choice to reach out, to care, to wonder, even in the silence. Because perhaps in the darkness between stars. It is not the signal that matters most, but the sender. And we are, all of us, the signal. In the end, our journey through the ladder of cosmic civilization is not just a climb through hypothetical technologies or unimaginable powers. It is a mirror held up to our own reflection. We began by imagining a life of perfect simplicity woven from the threads of complexity, where artificial intelligence tends to every need, where cities are clean, harmonious, and serene, and where intergalactic culture and knowledge pulse through our lives like breath, a world that feels like science fiction. And yet, with every scientific breakthrough we achieve, edges a little closer to science fact. It was a dream of what could be, not only for distant civilizations we may never meet, but for ourselves. If we learn to wield our intelligence with compassion and our power with restraint. From there, we ascended the Kardashev ladder, each rung a deeper plunge into awe. Type Y civilizations, masters of their planets, balancing weather, health, and cooperation with grace. Type 2 engineers, drawing every drop of energy from a star, building megastructures like Dyson spheres, not as fantasies, but as solutions. And Type 3, the galactic architects, no longer bound by biology or scarcity, but sculpting the stars themselves with intention and design. But just as the cosmos stretches further than we can see, so too does imagination. We followed that thread beyond Kardashev's vision into Type 4 beings shaping galaxies, Type 5 entities tapping into the multiverse, Type 6 masters of creation and destruction itself, and Type 7, those who transcend even existence, living in programmed realms of infinite renewal. And yet, as the scope expanded, so did our silence. We listened for others and heard nothing. We searched the skies and found only stars. And so we turned inward, toward Earth, and wondered if perhaps we are not the first, if deep beneath the layers of stone and time, the echo of another intelligence once walked this world and left only whispers. The Silurian hypothesis does not give us answers, but it humbles us. It reminds us that our current civilization, dazzling and dangerous, has only just begun and might just as easily vanish into the rocks if we forget to care for the world that made us. All of it draws us back to the oldest question, dressed in modern wonder. Are we alone? We may never know for certain. Perhaps others are out there, waiting, watching, choosing stillness over interference. Or perhaps they have never been. The universe may be filled with potential, yet untouched by parallel minds. But whether we are the first spark or just one in a constellation of civilizations, what matters most may not be what we find, but who we become in the search. Because the act of looking lifts us. It asks us to think beyond war, beyond borders, beyond fear. It dares us to believe in futures we cannot yet see and in lives we have not yet lived. The scale of stars dwarfs us, but the scope of our imagination elevates us. That is the paradox of being human. We are small, but we reach, fragile, but determined, alone, but always listening. So, as we conclude this voyage through imagined heights and forgotten pasts, through theoretical Dyson spheres and the intimate silence between stars, let us remember that wonder is a compass. Let us cherish the questions more than the answers, and the seeking more than the certainty. For in a cosmos as vast as this, the most extraordinary civilization may not be the one that builds megastructures or manipulates galaxies, but the one that looks up and chooses to wonder. And until we find a voice beyond Earth, let us be each other's signal, each other's light, echoing not just in the void, but in the shared hope that we are not alone because we are here together.